Hello and welcome to Calculus tutorial. Right now we are going to do something extremely important, as you can see in the middle of the screen, the fundamental theorem of calculus, one of the most important things we learn all year. It's important because it takes the indefinite integral and the definite integral and combines them. It sandwiches them together. It connects them into this thing called the fundamental theorem of calculus. We kind of touched on how these two are related when we talked about walking along at a constant velocity, but now we're going to point out that relationship explicitly. So, if you walk along with a constant velocity of 5, this would be your position curve if you happen to start at 5 feet or miles away, whatever it happens to be. And so we are going to connect the definite integral. So if we did the integral from 0 to 3 of our velocity function, which is 5, okay, which would be the area under the curve here, all the way up to there, which is, of course, 5 times 3 is 15. So how do we connect that 15 over here with our position curve, where your position is equal to the indefinite integral of velocity, which in this case is 5t plus c, but of course we're solving for the plus c, so it's plus 5. How are these connected? Where do we see the 15 over here? Well, we see the 15 by taking a look at how far we actually traveled over those 3 seconds. So after 3 seconds, we ended at 20. But since we started at 5, the actual distance we traveled was 15. That's how we see the definite integral in the indefinite integral. So where does that 15 come from? If you take the ending point and you subtract the starting point. If I take p at 3 minus p at 0, that is what gives me the 15. And so to put that into terms without position and velocity, we're going to call this one capital F, and we're going to call this one lowercase f for that relationship. So if you want to take the indefinite integral of lowercase f, that is the same as taking the indefinite integral f, taking the ending point, which in this case will be f at b, this is your ending point, and subtracting the starting point, which in this case will be f at a. And that, my friends, is the fundamental theorem of calculus. And that is important because now we can do a definite integral. We don't need geometric shapes. We don't need rectangles under the curve. We can simply take the antiderivative and then plug in the ending point and plug in the starting point, and that will give us our answer. It will actually shorten things quite a bit for us. You don't need to do Riemann sums or add up area of any kind. That powerful feature is why this is called the fundamental theorem of calculus. So let's see how that works algebraically, and you'll see it's not too bad. So I want to know the integral from -3 to 3 of this equation right here. So I don't want to use rectangles, so what I do is I take the antiderivative. The antiderivative here will be 1/3 x cubed plus 2x, and for this time we will put a plus c, but then we're going to plug in the ending point and the starting point and subtracted to. And the way we write that is we evaluate this from -3 to 3. You can just put them right there. So let's plug in the ending point. If I plug that in, 3 cubed is 27, divided by 3 is 9, plus 3 goes into there, so that gives us 6, plus c, minus, now plug in -3. -3 cubed is again 27, but a -27 divided by 3 is -9. -3 come in here, we get -6 plus c. Now here's where our algebra can sometimes mess us up. Don't forget that we are subtracting everything over here, so that negative always distributes. Okay? So that will become a +9, that will become a +6, and that will become a -c. And right now, can we just see that the c, we have a positive constant, and then we have the same constant but negative, and so that will go away. That always happens. You'll always have a c in the first one, and you'll always have a c in the second one. So you never need the plus c. When you're doing a definite integral, they will always cancel out. And then in front we still have a 9 plus 6. So 9 and 6 is 15, 9 and 6 is 15, 15 and 15 gives us 30. So that definite integral is equal to 30. Much easier than doing rectangles or geometric shapes, I'd say. Alright, but that works for trig functions as well. So let's try this. What is the integral from 0 to pi of cosine of x? Well, first take the antiderivative of cosine x, which is positive sine x. Another way to write this, you can put a vertical bar. That means evaluate. We're going to evaluate from 0 to pi. So you'll see the vertical bar there when you don't have big parentheses or brackets. If you already have a bracket, you don't need another vertical bar, so you can just put the numbers there. I've seen mathematicians write it both ways. Choose the one you like. So we're going to plug in pi, so we'll have sine of pi, not to be confused with the life of pi, minus sine of 0. Well, sine of pi, think about sine. Sine starts here, goes up, down, up. Pi is right here, so sine of pi is 0, minus sine of 0, well, that is right here. That is also 0. So this is equal to 0. And if that seems a little confusing, think about cosine. Cosine starts up here, goes down, down, up to there at 2 pi. Pi is right here in the middle. So we have this area that is then being canceled out by that area. And so in total, your area is 0. So hopefully that makes a little bit of sense for you. All right, algebraically, that's how it works. Hopefully that's not too bad. That makes taking definite integrals much easier. The fundamental theorem of calculus. All right, one more thing we want to take a look at, a motion example. This gets a little complicated because of the interpretation that you have to do. So you go out for a walk. At the end, you return home where you started. Your velocity can be modeled by this function. V is equal to sine of x. Interpret this math statement. What is the definite integral from 0 to 2 pi of your velocity? All right, so think about position, think about velocity. I'm going to draw it this way because velocity is sine of x. So if I just do the definite integral. V is sine, so the antiderivative of sine is negative cosine. And we need to evaluate that from 0 to 2 pi. I'm running out of room there, so I'll put it over here. So that will be negative cosine of 2 pi. Now, careful with your negatives, minus a negative cosine of 0. Cosine of 2 pi is 1. Minus a negative is positive. Cosine of 0 is also 1, so that is equal to 0. Now, what does this actually mean? What does that 0 mean? Well, that is talking about our distance in a way, because if we start with our velocity and we take an antiderivative, we're going backwards, we're talking about our position, we're talking about our distance. And before we've said that this is equal to how far you went, which hopefully seems a little weird. This isn't how far I went. I went somewhere and I came back home. I didn't travel 0. So what does this number mean? It's like your distance, only it has direction. This is your displacement. Okay, so I think the area here is 2 and the area here is negative 2. So if you walk forward 2 and you walk backward 2, how far did you go? One answer is 0 because you ended up where you started. That is called displacement. Now you could also say, well, no, you went 4 miles or 4 feet, whatever it happens to be, because you went forward 2, you went another 2 in a different direction. That's a total of 4. Technically, that's also correct. So if we were to take a look at this integral instead, the absolute value of v at t, that takes all the negatives and makes them positive. That would then give us 4, because the negative 2 would then become positive. That is your total distance. It's a fairly difficult interpretation to wrap your mind around, but this word displacement really helps give you the vocabulary for that. The fact that we went forwards and then backwards, those canceling each other out, and you starting back where you started, or ending where you started, is your displacement. If you want your total distance, you have to take all the negatives and make them positive, and that will give you how far you actually walked. But if you're using negatives, that tells you something called displacement. All right, the fundamental theorem of calculus. It is a powerful tool. Hopefully you can see it's not too hard to use, usually, but it can sometimes be hard to interpret.